All right, we're going to look at the table of standard reduction potentials. I'm going to go through this real quick, but then we're going to start examining the table itself and looking at all of these points. So just real quickly, when we look at this table, the E naught values are all for reduction reactions. The more positive the E naught, the more positive the half reaction potential, the greater its tendency for the substance to be reduced. The more it wants to be reduced, the more it wants to gain electrons, the more it wants to take electrons from something else, means the stronger it is at oxidizing something else. When we look at the table, we'll find at the top of the table is F2. F2 gas really wants electrons. It's a very strong oxidizing agent. It will take electrons from nearly everything. Li2 is Li plus is at the bottom of the table. It does not want electrons. It's a very weak oxidizing agent. And because Li plus is a very weak oxidizing agent, it means it's a strong reducing agent. It wants to put electrons on things. F minus is a very weak reducing agent. Okay. As we said before, the half cells are reversible. You can take any oxidation, any of these reduction reactions, and switch the sides of and make it an oxidation reaction. And when you do that, you change the sign of E naught, but not its value. All right. Under the standard state condition, something we'll get into, the diagonal rule. Anything that appears on the left of any half cell reaction will react spontaneously with a species that appears on the right of any half cell reaction below it on the table. We'll spend a lot of time on that. Don't worry about that. Okay, diagonal rule there. If you multiply the reaction by different coefficients, recall when we were balancing redox reactions, sometimes we'd have to multiply it by 3 or 2 to get the number of electrons to cancel. Multiplying it by stoichiometric coefficients does not change the value of the potential. If you have a ball, recall that if you have a ball up on the top of the hill here, if you have a ball on top of the hill, the potential energy is due to this distance here. If you have two balls up here, they each still have the same potential energy. So each individual one would have the same potential energy, so you do not multiply it by when you change coefficients. All right. So let's look at the table of reduction potentials and go through some of these things. So here we have it. It's on in the Tro book. It's page 909. And what we find, note this is the standard electrode potentials at 25 degrees Celsius, standard conditions. Note everything is written as a half reaction, everything is written as a reduction half reaction. At the top of the table is F2 gas plus 2 electrons goes to 2F minus. Fluorine gas really does not want to be fluorine gas. The reduction potential is 2.87 volts. It is our most positive reduction potential, meaning this reaction really wants to occur. This fluorine gas taking 2 electrons to become 2 fluoride ions is a reaction that really is spontaneous, really wants to happen. If we look at the bottom of the table, go way down, note here is SHE, our standard hydrogen electrode, set at 0 here. Lithium's at the bottom of the table. Aqueous lithium gaining an electron to form lithium solid has a potential of negative 3.04 volts. Recall, the more positive and the higher the value of a positive voltage, the more it's likely to happen. This is a negative voltage, which means this really doesn't want to happen. Lithium plus loves being lithium plus. It does not want to gain electrons to form lithium solid. And that's what we can expect down here. Note we've got a lot of our alkaline earth metals down in this region here. They really don't tend to want to be in the metallic form that much. They really would prefer to be ions. Okay. So all these are reduction potentials, but what would happen if you reversed this lithium reaction? You wrote lithium solid goes to Li plus an electron. Well, if you reverse a reaction, what do? You change the sign and it becomes positive 3.04 volts, which is a reaction that's very, very likely to occur. Lithium solid losing an electron to form lithium plus ions is very, very likely to occur. Now, a very important part of this table that's going to help you figure out what happens, whether reactions are spontaneous, is our diagonal rule, which states anything on the left side will react spontaneously with anything on the right side and below it. Okay, that's our rule. For example, we had our copper and zinc electrodes. And if we look, okay, where's copper 2 plus and where is zinc solid? Well, our reaction was copper 2 plus 2 electrons goes to copper solid. That was our reaction. Note, there's another copper in here. Copper 2 plus 1 electron goes to copper 1 plus. But that's not the reaction that occurred. Our copper 2 plus gained 2 electrons to form copper solid. So copper is right here. So copper 2 plus is on the left side, which means copper 2 plus will react spontaneously with anything to the right and below it. And we know copper 2 plus to the right and below it is tin. Okay, there is our, well, there's tin, but what do we have? Zinc. Oh, yeah, we had zinc. Okay, there's zinc below it. So it'll react with tin, it'll react with zinc. Okay, so when you're looking at this table, it means two things. It means if we set up two half-cell reactions, if we set up our galvanic cell, we could put copper 2 plus and copper solid on one side, zinc 2 plus and zinc solid on the other side. And the copper 2 plus we know will gain the electrons because it will react spontaneously with our zinc solid, which will lose the 2 electrons. It also means what would happen if I threw in a piece of zinc into copper 2 plus solution? Well, we know the copper 2 plus would react with the zinc. So we can use this to say, all right, what would happen if I threw in a piece of solid iron into a solution of lead 2 plus? Okay, solid iron, lead 2 plus. I need to find them on the table. Well, there's iron solid right there. Where's lead 2 plus? Lead 2 plus, lead 2 plus. It is, oh, it's here. Question, if I threw a piece of iron into lead 2 plus solution, will iron react with lead 2 plus? Well, nope. Solid iron is to the right and below lead 2 plus. So yes, if I had a lead 2 plus solution, I know that if I threw in a piece of solid iron, it would react. And it also tells me what the products would be. If I had a piece of solid iron, throw it in lead 2 plus solution, the lead 2 plus will be reduced to lead solid. The iron solid would be oxidized to iron 2 plus. So this table will tell you what will react with what and what the products are also. So that's cool. What if I had, say, a piece of lead and I put it in a zinc 2 plus solution? What would happen if I had a piece of lead and mixed it with zinc 2 plus? Well, where's lead solid? Where's zinc 2 plus? Lead solid, well, this is lead 2 plus. Lead solid. Lead solid's right here. Where's zinc 2 plus? We look, oh, there's zinc 2 plus. Note, wait, here's lead solid, here's zinc 2 plus. Is one of them to the right and below the other? No, lead solid's here, so there's nothing to the right and below it. Here's zinc 2 plus. Here's to the right and below it. No, lead solid is not to the right and below zinc 2 plus. We don't have that relationship, which means if I took a solid piece of lead, threw it into aqueous zinc, nothing would happen. There would be no reaction. Cool. All right, so very nice table that tells you what's going on. It also tells you, okay, basically how reactive things are. We know because it's at the top of this table, F2 gas is very reactive. Hydrogen peroxide is very reactive. How do I know hydrogen peroxide is very reactive? Because anything to the right and below it will react with it. And looks, what's to the right and below hydrogen peroxide? A whole ton of stuff is to the right and below hydrogen peroxide. Note, how reactive are calcium ions? How reactive are calcium ions? Well, let's find calcium ions. They're right here. They will react spontaneously with anything to the right and below them. Well, that's only 3 things on this table. So we know calcium ions are really not all that reactive. Note, and by the same token, we know that anything here will react spontaneously with anything to the left and above it, because our diagonal goes this way. Anything over here on the left reacts with anything to the right and below. Therefore, anything on the right will react with anything to the left and above. So note, what will react with solid sodium? All this stuff will react with solid sodium. Cool. So that's a nice feature of this table. So we can use this and to figure out, okay, let's see. Here's an interesting problem using this table. I'm going to set up a galvanic cell, an electrochemical cell, and with my 2 electrodes, my 2 half reactions, I'm going to have a solid piece of gold and gold 3+ in solution. And I'm also going to have in the other beaker a solid piece of silver and silver plus in solution. And the question is, what's going to happen? Well, what's going to happen is just a very general question, so let's be specific. Here looks like a nice potential exam question here. All right. If I have my